So let me just, before we dive into lots and lots of technical details, let me try to give you at least some inspiration for why we care about these details. I'm an applied mathematician, and many of you are some version of applied mathematician too, physicist, statistician, something like that. We have some equations that we want to solve that govern whatever process we're interested in. We can't do it exactly, so we use some kind of iterative procedure. Maybe it's Newton's method. It might involve taking our continuous domain we're interested in and discretizing it. And then we start iterating things, and we're hoping that as we iterate, we get closer and closer to whatever we're hoping to compute. Does it converge? So this really boils down to, we need techniques for proving that we're actually converging to the solution of some problem that we actually care about. A really important tool for doing that is this concept of compactness. We very briefly talked about compactness in one dimension last semester. Does anyone remember how we defined a compact set? Closed and bounded. So for sets of real numbers, we define compactness as closed and bounded. Actually, for sets in Rn, you can define compactness as closed and bounded too. There's another equivalent way of interpreting compactness, which is called the Heine-Borel Characterization. It's far less intuitive, and it's what we're going to talk about today. And I will do my best to provide at least a little bit of intuition for what's going on. Because despite the fact that it's less intuitive, it turns out to be more useful for proving the kinds of things we want to prove, like that we can have sequences that converge to hopefully what we want. And it turns out when you go beyond Rn to other spaces, maybe you want spaces of continuous functions or continuously differentiable functions, so you're trying to solve a differential equation. Closed and bounded is simply not the right way to think about compactness. It doesn't do what you want it to do. And we'll see that towards the end of the semester when we get into chapter 8. So right now we're laying some of the groundwork for things that will become very important later in the semester, but will also help us prove interesting things in Rn. So I said we're interested in convergence of sequences, so let's just remember what we mean by sequences and convergence. This part is not substantially new. Okay, so if we have a sequence of points, okay, let's call it xm. Okay, and these are all vectors now. Okay, and we can talk about these converging to a limit, and it's enough just to say that, well, each component converges. Okay, so there's nothing new in the definitions here. We're going to say that the limit as m goes to infinity of xm equals x if, there's different ways of writing this. We could say if the distance between these two things goes to 0. Or equivalently, the components converge. So equivalently, we could say, well, the first component of the elements in our sequence, right? We have a sequence of vectors. If we just look at the first components, we're down to a sequence of real numbers. This converges to the first component, and so on. Sorry, it's xn. And we had a nice way of characterizing convergence, right? This was the definition, but to check the definition, you have to be able to guess what the limit is. If we wanted to check if a sequence converges without needing to guess at the limit, there was a condition for that. Any takers? This is the one that everybody forgets when I ask it consistently. So we had this Cauchy condition that said, let's look at different terms in the sequence, and instead of comparing the terms in the sequence to the limit, we'll compare the terms in the sequence to other terms in the sequence and require that to get small quickly enough. So we have this Cauchy criterion. Okay, so we're going to say that this sequence converges if and only if. All right, and then we had something that was down to our usual, epsilon and star kind of definition. If for all epsilon greater than 0, there exists some n star, such that. And then we said instead of comparing to a limit, we're going to compare any two values in the sequence that are beyond n star. So such that if n and k are beyond n star, then the distance between these two values is less than epsilon. Right, so this should look familiar. This is the same Cauchy criterion we had in 1D, except now this is a distance instead of just a scalar inside of here. So that's sequences. Now we're talking about compactness. We want to be able to, sets can look strange. If you have a circle, you know what the diameter of a circle is. But in general, we're going to say the diameter of a set is just the farthest possible distance between 2 points in that set. Right? That captures what we expect the diameter of a circle to be, but it extends to much more general sets. So we're going to say if S is a non-empty set, then the diameter is going to be defined this way. Okay, so what we're going to do is take any 2 points in the set and see how far apart they are. And then we do that for every other possible combination of 2 points in the set. Okay, so we're going to look at, I'll leave a little gap here, the distance between these 2 points in the set. And now what are we going to do? We want to find the biggest possible distance. We shouldn't assume that a maximum exists, so we're going to take the supremum of all of these possible distances. Right? So this, for any x and y, this is a real number. So we expect to be able to compute a supremum, which could be infinite, or it could be finite. So we're going to take this supremum. And we're going to call this the diameter. Okay? And again, the diameter is just the farthest apart 2 points in a set can be. Okay, and if, again, the supremum could be finite, it could be infinite. If the supremum is finite, then we say, great, we have a bounded set. There's only so far apart points can be. If the supremum is infinite, then it's an unbounded set. Okay, so a set S is bounded if this is finite. We're happy with terminology so far? All right, so let's jump in. I'm going to start with a little technical lemma, which we're going to use to prove our main result about compactness. So this has to do with nested sets. I'll write the lemma, and I'll try to draw a little picture to go along with it. And this is going to be a key point in our main argument. So let's suppose we have a sequence of nested sets. And they're closed. Closed and non-empty. Okay, and they're nested in this way. So S1 is the biggest set. Then S2 is the next set, lives completely inside of S1. S3 lives completely inside of S2, and so on. And we have a sequence of these sets. There's infinitely many of them, and they keep being contained in the previous ones. And the diameter of these sets shrinks, and it's shrinking to 0 in the limit. So the limit of this diameter is 0. Okay, then what essentially happens, these sets are going to shrink down to a single point, and that point is going to be contained in all of these sets. That's the result. So we're going to say then there exists a point x that lives in the intersection of all of these sets. Okay, so here's the picture. I have my first set, S1. S2 is completely contained in S1. S3 is completely contained in S2. So we're getting smaller and smaller sets. I mean, you could have sets that are contained within each other but still stay big in some sense. But that's not what's happening here. The diameter of these sets is going to 0. And what this lemma says is there's a point in here that we call x, and this point lives in all of the sets. Which, by the way, this wouldn't happen with open sets. If you tried to do this with open sets, you're not going to be guaranteed that you actually have a point that lives in all of these sets. So if I tried to do this with open sets, here's my number line. I might have 0 to 1 as my first set, 0 to 1/2 as my second set, 0 to 1/3 as my next set. And these sets are contained within each other, and they're shrinking down. They're shrinking down to this point 0. But the point 0 is not contained in any of these sets. Okay? So there's a distinction here that happens with closed sets, and that's important. That not only are these shrinking down to a point, they're shrinking down to a point that was actually contained in all of these sets. And of course, if I changed these to closed and included the endpoints here, again, they'd be shrinking down to 0, and then 0 would be contained. So the fact that this is closed is important. Yeah?
So what if the diameter was going to some non-zero number, but smaller than the first set in the sequence?
If it was going to some non-zero number, then I guess you would still have something that's contained in all of these. Yeah. Okay, so let's just try to sketch out this result. I hope an example like this provides a little intuition, at least into why this is a reasonable thing and why the conditions are reasonable, that we need a closed set. Okay, so we have this set. Now what I'm going to do, yeah?
Even in Rn, the union of the intersection of closed sets is closed.
The intersection of closed sets is closed, yeah. So then the question is it a closed set that contains a point, or is it the empty set, which is also closed? But yes. So what I'm going to do is create a sequence of points here. So I'm going to have a point x1 that lives in my first set. I'm going to have a point x2 that lives in my second set. Pick a point x3 that lives in my third set. And what I'm going to argue is that these points converge to a limit, and that the limit lives inside all of these sets. Okay, so let's let xm being contained in Sm be a sequence of real numbers, of vectors in Rn, sorry. Okay, so I want to show that this converges. I have no number or vector to pull out of my hat to use as a candidate for the limit. So I'm going to show it converges using my Cauchy criterion by showing that things get closer together. They should get closer together Because once we go far enough down the sequence, x3 is contained in S3, everything else is also contained in S3, and the diameter of S3 is whatever it is. As we go farther and farther, they're going to be contained within this diameter that's getting smaller and smaller and going to 0. So that's the picture. This is why this is going to work. Okay, so let's let epsilon be bigger than 0, like our standard way of starting a proof in analysis if we don't know what else to do. And introduce an epsilon, which again is a completely natural thing to do because we're trying to prove convergence, and the Cauchy criterion is the main tool we have. All right, so we're expecting to force these points to lie within some diameter. The diameter we can be made less than epsilon as long as we're far enough away, far enough down the sequence, because the diameter goes to 0. Okay, so there exists some k such that the diameter of Sk is less than epsilon. We know that. It's because these diameters go to 0. Okay, so let's let let's say m and p be bigger than k. This is where we start running into the notational issues that will continue to plague us in all of math, that we run out of letters in a big hurry and try not to reuse them. So if we're beyond this, then xm and xp, they both belong to Sk, right? All right, so say my k was 2. I said k is 2. I've picked m and p beyond that. So as long as I've gone beyond that, I'm always going farther inside, farther inside, farther inside. So these later points live in that original set. And that means the distance between them is at most the diameter of this set. Right? It's how the diameter is defined. It's the farthest apart 2 points can be. And this is less than epsilon. And that's our Cauchy criterion. Okay, I changed notation from here, I guess. But this is our Cauchy criterion, that as long as m and p are chosen belong k. So again, I changed the notation. The k there is standing in place of this n star. And as long as we're beyond that, the distance between these is less than epsilon, which means the limit of this sequence exists. Now, what do we want to know? We want to know that this x lives inside all of these sets, that it lives in the intersection of all of these sets. All right, so let's pick any k and try to argue that x lives in this set, right? Which again, with open sets, this wouldn't happen necessarily. So it's going to be important that the set is closed. We'll have to use that somewhere. We know we have to use that somewhere. So let's pick any k, and we want to show that x belongs to Sk. So let's see, what do we know? Well, we know that xk belongs to Sk. Also, xk plus 1 belongs to Xk. All these later points also belong to Sk. So we have a collection of points that all lie in Sk, and they converge. There's another way of thinking about that. That means x is a limit point of this set. Okay, so here's our SK. Here's x1, x2, x3, x4. We know they're converging to something. The fact that we're converging to something, call that x, means that if I draw any neighborhood around here, I can find a point that lies in that neighborhood, no matter how small. And all of those points lie in SK. So x is a limit point of SK. X being the limit of this sequence, x is the limit of a sequence that lies entirely in SK. And that's totally equivalent to saying x is a limit point of SK. Well, this is good. We know something about the limit points of closed sets. In fact, is another way of characterizing a closed set. A set is closed if and only if it contains all of its limit points. And that hasn't changed from one dimension, and the proof doesn't change from one dimension. So since S is closed, since SK is closed, we must have that it contains this limit point. And that's it. That's the proof. We found this x. The sequence converges to this x. It's contained in all of these sets, right? It's contained in this particular SK, but I could have chosen any k I want. There was nothing special about this particular k. It didn't have to be particularly big. It just was whatever it is. So that's all we need. This is true for all k. And that's our proof. We've identified this point now that lives in every single one of these sets. So it lives in the intersection. And we're done with this little technical lemma. Yeah?
Is it unique?
It is actually unique, yeah. You can show it's unique. We're not going to need that it's unique, but yes, it will end up having to be unique.
We didn't prove that's unique.
We did not prove that it's unique, that's right. What you can end up arguing is that for any epsilon, if you take k big enough, x minus y could be made less than epsilon for any y in SK, and then you take that to 0 and find that, well, if x minus any other point in that set, it can be made less than any epsilon, it's 0. So yeah, it is unique. Other questions? All right, this feels like a divergence. It is a little bit, but we're going to need this lemma. So let's hold this in the back of our head. I wanted to do it here rather than interrupt in the middle of the discussion of compactness with this and risk losing our train of thought there. Let's come back to compactness. So you've told me that a compact set is closed and bounded, and that's absolutely true. That's still the definition of compactness in Rn. In Rn. It is not the way we define compactness in more general metric spaces, but it does work in Rn. Okay, so a set S contained in Rn. This part is really, really, really important to the definition. Is compact if it is closed and bounded. All right, now this is great. This is useful in Rn. It's not useful later for more general metric spaces, and it's still from just these hard to directly prove a lot of the things that we want to prove. So we need a different characterization. So let me introduce a little bit more of the language we need to build up our alternate characterization. We need this concept of an open cover. So I'm going to define it, and I'll write down a couple examples, and we can see what's going on. So we start with a collection of open sets. I'll call it script H. So script H is a set of sets. It's a set of open sets in particular. We're going to call it an open covering of S. If S is contained in the union of all of these sets. Okay, so we have a set of sets, a set of open sets, and collectively, these open sets contain all of the points in S. All right, so if this is my S, there's tons of ways I could do this. I could just draw one big open set around all of this. I could just let Rn be my open cover, in fact, a single set. So there could be a single set in this collection. I could break it down in different ways. I could have a lot of different, I could just try to cover this thing with balls of radius 1 if I wanted to. Or I could do this in different ways. I could even say, let's try to make there be infinitely many of these and let them become arbitrarily small in some places. So I could have a bunch that just become smaller and smaller and smaller. But taken together, I'm going to require that S lives in the union of all of these things. Okay, again, there's many different ways we could do this. We could have one set in our open cover. We could have infinitely many. They could all be relatively big sets. They could become arbitrarily small. We might have open sets with arbitrarily small diameters. You pick any epsilon, I can find an open set that has diameter less than that. So we can cover these in complicated ways. The result that we're going to have is that if S happens to be a compact set, closed and bounded in Rn, then even if I start with a ridiculous cover that consists of infinitely many sets, and some of them are arbitrarily small, that there still will be a way to pick finitely many of them and still cover our set. So let me do a couple of 1D examples with pictures, because this is in no way obvious. So let's suppose my set is the open interval from 0 to 1. And my open cover is going to be all intervals of the form 1 over n plus 2 to 1 over n. Okay, so here's my interval. The first set in here is, I guess, 1/3 to 1. The next one is going to be 1/4 to 1/2. I'm going to stagger the way I draw these a little bit, because otherwise you won't be able to tell which endpoints are belong with which set. Uh, 1/5 to 1/3. Right, and so on. I'll do one more. Now, taken together collectively, these manage to cover the entire interval from 0 to 1, the entire open interval. So this is an example of an open covering of S. Now, there's infinitely many sets in here, right? And they become arbitrarily small. As n gets bigger and bigger, the length of this interval gets smaller and smaller and smaller. and the length of the interval approaches 0 as we get closer and closer to here. Now, you might ask, this is a small interval. It's just the interval from 0 to 1. Do I really need to use all of these infinitely many sets to cover it? But if you start looking at this and asking yourself, well, which sets should I take out, you'll start to realize, actually, they're all necessary. I can't start removing sets and still cover my interval. So for example, I might say, well, isn't this interval from 1/4 to 1/2 really doing the same work as this interval and this interval? But the answer is no, not quite. This is the only interval that contains the point 1/3. If I pull out this set, I've lost the point 1/3. Okay, if I pull out this set here, well, I've lost the point 1/4, which is an endpoint of 2 other intervals, but it's not contained in them. So it turns out if I remove any one of these sets, I don't have an open cover anymore. I really need all of the infinitely many of these. So if we remove any one set from H, we don't have an open cover anymore. And this, it turns out, is really the essence of a set being not compact. So it turns out if a set is compact, you can remove sets. You can remove lots of sets and get yourself down to only finitely many of these. Whereas for this open set, this non-compact set, and we know it's not compact, it's not closed, we can't just start pulling sets out, or at least we're not guaranteed to. Of course, there's other ways of coming up with open covers. I could say my open cover is just the set itself, one set. You can do that. But there's also ways of finding these more pathological covers where I just can't start removing sets. I just can't. So let's see what changes when I include the endpoints in here. I'll make this set closed. So now S is the closed interval. This is compact now, closed and bounded. I'm going to build an open cover. I'll start from the same open cover that I had here, but of course I need to add a little bit more in here because I would now need to be able to cover the endpoints as well. So let's let H be, we'll start with this. My pathological open cover where things get smaller and smaller. But now I need to also include the endpoints. So I'll pick an epsilon and go from minus epsilon to plus epsilon. So some little tiny open set that covers this, and then I need some little open set that covers this. So I guess 1 minus epsilon to 1 plus epsilon. And now I'm in business. I have an open cover again. doesn't contain any other point. Now I'm going to use all of these little balls that I just drew here and say, hey, that looks like an open covering of my set. But once I've drawn a little neighborhood around each set, a little open neighborhood, I've got an open cover. Right? Each point is contained in exactly one of these open sets. So H is the collection of all of these neighborhoods. Is an open covering. So I'm hoping to use the Heine-Borel theorem here. That's the point of putting this here and trying to show that it's useful. Heine-Borel says I need to start with a compact set, closed and bounded. Well, we started with a bounded set. Is it closed? You're nodding. Why is it closed?
I'm just thinking if every point's an isolated point, then I mean, I can't really formalize it.
Yeah,
Like,
so
I can see it.
you're almost exactly said it. Somebody else want to take a stab at it?
Contains all the limit points.
It contains all its limit points, of which there are none. So S contains all its limit points. Okay, there are none, so trivially. Set of limit points is the empty set, which is certainly contained in S. So S is closed. Okay, S is also bounded. That was one of our hypotheses. So we start with a bounded set. So S is compact. So by Heine-Borel, we know that we should be able to extract finitely many of these. Okay, so it means that there should exist x1, x2, some finite collection, such that S is contained in the union of this finite collection of open neighborhoods. Right, so everything in my open cover has the form of a ball around X. Heine-Borel says finitely many of them will do the trick. There's a problem though. We know that each of these neighborhoods contains exactly one point in X. They were chosen, but because these points are all isolated points, they were chosen to contain only one point. Okay, so this is our problem here. Each of these neighborhoods contains exactly one element of S. So the fact that S is contained in this set means that S can only be x1, x2, x3, up to xk. It has to be one of those. So if x belongs to S, then x equals x1, or x equals x2, or x equals xk. And this is a problem. this is a problem because the hypothesis of our theorem said we're starting with S being bounded, but also infinite. It has infinitely many values. And we've just shown that we can only possibly have finitely many values. So this contradicts S being infinite. So what did we do? We started with this assumption that S has no limit point, and we've seen that that leads us into absurdity. So it must be a bad assumption. We must be able to say that actually S does have a limit point. So in other words, if I start, let's do 1D. If I start with a bounded interval, I say I'm going to put infinitely many points in here, but they're bounded. They can't leave here. So I just start throwing down points anywhere I want in here. The fact that there are infinitely many of them means eventually they have to build up somewhere. They can't just keep staying separated from each other. There's not enough space for them to stay separated from each other. And that, again, means that if this collection of points happens to come from a numerical method, they also have to build up somewhere. They have to converge to something. Questions? So we're going to revisit these concepts again in chapter 8. In more general metric spaces, this is the definition of a compact set. Closed and bounded doesn't have anything to do with the definition anymore because it's no longer equivalent, so you have to pick one or the other. In Rn, they're equivalent. Later on, not equivalent, so you've got to pick one. This is the one that feels harder to work with, but is more useful, and with particular metric spaces, we'll do what we did for Rn. Rn, we said, what's an easier way of characterizing this, closed and bounded? You can do that for other metric spaces. You can say, we want compactness for my particular metric space. Maybe there's some easier ways of characterizing that, and there are. And we'll see that for, say, the space of continuous functions. There are ways of characterizing compactness that are easier than Heine-Borel, but give us access to the power of this theorem. So that's it for today. Next class, we're going to go into more calculus. So we'll start building up limits and continuity, and that stuff will feel much easier than this. That stuff is more of a straightforward generalization of what we did in one dimension.